Human Physiology, Physiology Introduction. The word physiology is from the ancient Greek, meaning natural philosophy, and it is the study of how organisms perform their vital functions. An example is the study of how a muscle contracts or the force contracting muscles exert on the skeleton. It was introduced by French physician Jean Fernery in 1552. Physiology is built upon a tripod of sciences: physics, chemistry, and anatomy. Types of human physiology. Human physiology is the study of functions of the human body that can be divided into the following types. Cell physiology. This is the cornerstone of human physiology. It is the study of the functions of cells. Special physiology. This is the study of the functions of specific organs. For example, renal physiology is the study of kidney function. Systemic physiology. It includes all aspects of the function of the body systems, such as cardiovascular physiology, respiratory physiology, reproductive physiology, etc. Pathophysiology. It is the study of diseases on organ or system functions. Pathos is the Greek word for disease. Levels of organization. Atom. An atom is the smallest particle of an element or molecule. Molecule. A molecule is a particle composed of two or more joined atoms. Macromolecule. A macromolecule is a large molecule, such as carbohydrates, lipids, proteins, or nucleic acids. Organelles. An organelle is a small organ of a cell which performs a particular function. For example, the cell membrane, and cytoplasm, and nucleus. Cell. The cell is the basic unit of structure and function of living organisms. Tissue. A tissue is a group of similar cells that perform a specialized function. For example, epithelia, connective, muscle, and nervous. Organ. An organ is a structure consisting of a group of tissues that perform a specialized function. For example, the skin, heart, brain, etc. System. A system is a group of organs that act together to perform a specialized function. Cardiovascular system, respiratory system, or urinary system, for example. Human body. A living organism is the most complex level of organization. It consists of all the systems arranged in a discrete manner so as to facilitate functioning of the various organ systems in synchronicity. The 7 characteristics of life. Cells. All living organisms have cells. Cells are the building blocks of life. Metabolism. All living organisms eat, drink, breathe, and excrete. Growth. All living organisms take in material from the environment to enlarge and sustain. Reproduction. All living organisms are able to produce a copy of themselves. Irritability. All living organisms are able to react to a change in their environment. Adaptation. All living organisms are able to compete with each other for food and space to survive. Movement. All living organisms are able to move. Cell's physiology. The cell is the basic unit of all living organisms. The cell is the functional unit of an organism. Cells are not all the same, but all cells share general structures. Cells are organized into 3 main regions: nucleus, cytoplasm, and plasma membrane. The nucleus. It is the center of the cell because it contains genetic material, DNA. It consists of 3 main regions: the nuclear membrane, the nucleolus, and chromatin. The nuclear membrane serves as a barrier of the nucleus. It consists of a double phospholipid membrane and contains nuclear pores that allow for the exchange of material with the rest of the cell. Nucleolus. The nucleus contains 1 or more nucleoli. It functions as the site of ribosome production. Ribosomes then migrate to the cytoplasm through nuclear pores. In chromatin, it is composed of DNA and protein scattered throughout the nucleus. Chromatin condenses to form chromosomes when the cell divides. Plasma membrane. It is the barrier for cell contents. It consists of double phospholipid layer and a monolayer of protein scattered around the phospholipid layer. Other materials in plasma membrane include cholesterol and glycoproteins. Cytoplasm. It is the thick jelly-like fluid. It represents the material outside the nucleus and inside the plasma membrane. It consists of cytosol. Cytosol is the fluid that suspends the other elements, the organelles. Organelles perform the metabolic activity of the cell. The cytoplasmic organelles are the organelles which are present and are scattered in the cytoplasm. They perform specific functions. Ribosomes represent sites of protein synthesis in the cell. They are found at two locations, free in the cytoplasm and attached to the endoplasmic reticulum. The endoplasmic reticulum itself are fluid-filled tubules for carrying substances, of which there are two types. The rough endoplasmic reticulum carry ribosomes that represent the sites of protein synthesis. The smooth endoplasmic reticulum function in cholesterol synthesis and breakdown, as well as fat metabolism and the detoxification of drugs. The Golgi apparatus modifies and packages proteins, secretes vesicles, as well as plasma membrane components and lysosomes. Lysosomes contain enzymes that digest non-usable materials within the cell. Peroxisomes are membranous sacs of oxidase enzymes. They detoxify harmful substances and break down free radicals. Mitochondria are the powerhouse of the cell. They can change shape continuously. They also carry out reactions where oxygen is used to break down food to provide ATP for cellular activities. The centrosome is composed of two centrioles surrounded by an amorphous mass of protein. Centrosomes are associated with the nuclear membrane during prophase of the cell cycle. In mitosis, the nuclear membrane breaks down and the centrosome can interact with the chromosomes to build the mitotic spindles. Centrioles are the self-replicating organelles made up of 9 bundles of microtubules. They appear to help in organizing cell division, but aren't essential to the process. Cytoskeleton is a network of protein structures that extend throughout the cytoplasm. It provides the cell with an internal framework. For instance, there are 2 components, the microfilaments and microtubules. Microfilaments are solid rods made of proteins called actin. These filaments are important support structures for the cytoskeleton. Microtubules are straight, hollow cylinders that are found throughout the cytoplasm of all human cells and carry out a variety of functions, ranging from transport to structural support. Cell membrane is made up of lipids, proteins, and carbohydrates. Human Physiology, Chapter 2, Homeostasis. The human organism consists of trillions of cells, all working together for the maintenance of the entire organism. While cells may perform very different functions, all the cells are quite similar in their metabolic requirements. Maintaining a constant internal environment with all that the cells need to survive, oxygen, glucose, mineral ions, waste removal, and so forth, is necessary for the well-being of individual cells and the well-being of the entire body. The varied processes by which the body regulates its internal environment are collectively referred to as homeostasis. What is homeostasis? Homeostasis, in a general sense, refers to stability or balance in a system. It is the body's attempt to maintain a constant internal environment. Maintaining a stable internal environment requires constant monitoring and adjustments as conditions change. This adjusting of physiological systems within the body is called homeostatic regulation. Homeostatic regulation involves three parts or mechanisms. 1. The receptor. 2. The control center. And 3. The effector. The receptor receives information that something in the environment is changing. The control center, or integration center, receives and processes information from the receptor. And lastly, the effector responds to the commands of the control center by either opposing or enhancing the stimulus. This is an ongoing process that continually works to restore and maintain homeostasis. For example, in regulating body temperature, there are temperature receptors in the skin which communicate information to the brain, which is the control center, and the effector is our blood vessels and sweat glands in our skin. Because the internal and external environments of the body are constantly changing, and adjustments must be made continuously to stay at or near the set point, homeostasis can be thought of as a synthetic equilibrium. Since homeostasis is an attempt to maintain the internal conditions of an environment by limiting fluctuations, it must involve a series of negative feedback loops. Positive and negative feedback. When a change of variable occurs, there are two main types of feedback to which the system reacts. Negative feedback, a reaction in which the system responds in such a way as to reverse the direction of change. Since this tends to keep things constant, it allows the maintenance of homeostasis. For instance, when the concentration of carbon dioxide in the human body increases, the lungs are signaled to increase their activity and expel more carbon dioxide. Thermoregulation is another example of negative feedback. When body temperature rises, receptors in the skin and the hypothalamus sense a change, triggering a command from the brain. This command, in turn, affects the correct response, in this case, a decrease in body temperature. Home heating systems versus negative feedback. When you are at home, you set your thermostat to a desired temperature. Let's say today you set it at 70 degrees. The thermometer in the thermostat waits to sense a temperature change either too high above or too far below the 70-degree set point. When this change happens, the thermometer will send a message to the control center, or thermostat, which in turn will send a message to the furnace to either shut off if the temperature is too high or kick back on if the temperature is too low. In the home heating example, the air temperature is the negative feedback. When the control center receives negative feedback, it triggers a chain reaction in order to maintain room temperature. Positive feedback. A response is to amplify the change in the variable. This has a destabilizing effect, so it does not result in homeostasis. Positive feedback is less common in naturally occurring systems than negative feedback, but it has its applications. For example, in nerves, a threshold electric potential triggers the generation of a much larger action potential. Blood clotting, in which the platelets process mechanisms to transform blood liquid to solidify, is an example of a positive feedback loop. Another example is the secretion of oxytocin, which provides a pathway for the uterus to contract, leading to childbirth. Harmful positive feedback. Although positive feedback is needed within homeostasis, it can be harmful at times. When you have a high fever, it causes a metabolic change that can push the fever higher and higher. In rare occurrences, the body temperature reaches 113 degrees Fahrenheit, or 45 degrees Celsius, and the cellular proteins stop working. Then metabolism stops, resulting in death. Summary: sustainable systems require combinations of both kinds of feedback, generally with the recognition of divergence from the homeostatic condition. Positive feedbacks are called into play, whereas once the homeostatic condition is approached, negative feedback is used for fine-tuning responses. This creates a situation of metastability, in which the homeostatic conditions are maintained within fixed limits, but once these limits are exceeded, the system can shift wildly to a wholly new and possibly less desirable situation of homeostasis. Homeostatic systems have several properties. They are ultra-stable, meaning the system is capable of testing which way its variables should be adjusted. Their whole organization, internal, structural, and functional, contributes to the maintenance of balance. Physiology is largely a study of processes related to homeostasis. Some of the functions you will learn about are not specifically about homeostasis. For example, how muscles contract. But in order for all bodily processes to function, there must be a suitable internal environment. Homeostasis is, therefore, a fitting framework for the introductory study of physiology. Cruise control on a car as a simple metaphor for homeostasis. When a car is put on cruise control, it has a set speed limit that it will travel. At times, this speed may vary by a few miles per hour, but in general, the system will maintain the set speed. If the car starts to go up a hill, the systems will automatically increase the amount of fuel given to maintain the set speed. If the car starts to come down a hill, the car will automatically decrease the amount of fuel given. It is the same with homeostasis. The body has a set limit on each environment. If one of those limits increases or decreases, the body will sense and automatically try to fix the problem in order to maintain the preset limits. This is a simple metaphor of how the body operates. Constant monitoring of levels and automatic small adjustments when those levels fall below or rise above a set point. Integumentary system. The integumentary system, the skin, is involved in protecting the body from invading microbes, mainly by forming a thick, impenetrable layer, regulating body temperature through sweating and vasodilation, vasoconstriction, or shivering and piloerection, or goosebumps, and regulating ion balances in the blood. Stimulation of mast cells also produce changes in blood flow and capillary permeability, which can affect the blood flow in the body and how it is regulated. It also helps synthesize vitamin D, which interacts with calcium and phosphorus absorption needed for bone growth, maintenance, and repair. Hair on the skin guards entrance into the nasal cavity or other orifices, preventing invaders from getting further into our bodies. Our skin also helps maintain balance by excretion of water and other solutes. For example, the keratinized epidermis limits fluid loss through skin. It also provides mechanical protection against environmental hazards. We need to remember that our skin is integumentary and is our first line of defense. The skeletal system. As the structural framework for the human body, the skeletal system consists mainly of the 206 or so bones of the skeletal system, but also includes cartilages, ligaments, and other connective tissue that stabilize and interconnect them. Bones work in conjunction with the muscular system to aid in posture and locomotion. Many bones of the skeleton function as levers, which change the magnitude and direction of forces generated by skeletal muscle. Protection is a pivotal role occupied by the skeletal system, as many vital organs are encased within the skeletal cavities, cranial and spinal, and bones form much of the structural basis for other body cavities, the thoracic and pelvic cavities. The skeletal system also serves as an important mineral reserve. For example, if blood levels of calcium or magnesium are low and the minerals are not available in the diet, they will be taken from the bones. Also, The skeletal system provides calcium needed for all muscular contraction. Finally, red blood cells, lymphocytes, and other cells relating to the immune response are produced and stored in the bone marrow. The muscular system. The muscular system is one of the most versatile systems in the body. The muscular system contains the heart, which constantly pumps blood throughout the body. The muscular system is also responsible for involuntary, for instance, goosebumps, digestion, and breathing, as well as voluntary, walking or picking up objects, actions. Muscles also help protect organs in the body cavities. The muscles in your body contract, which increases your body heat when you are cold. The act of shivering occurs when the internal temperature drops. Muscles around vital organs contract, breaking down ATP and thereby expanding heat, which is then distributed to the rest of the body. The cardiovascular system. The cardiovascular system, in addition to needing to maintain itself with certain levels, plays a role in the maintenance of other body systems by transporting hormones. The heart secretes atrial natriuretic peptide and brain natriuretic peptide, or ANP and BNP respectively, and nutrients such as oxygen or EPO to bones, taking away waste products and providing all living body cells with a fresh supply of oxygen and removing carbon dioxide. Homeostasis is disturbed if the cardiovascular or lymphatic systems are not functioning correctly. Our skin, bones, muscles, lungs, digestive tract, and nervous, endocrine, lymphatic, urinary, and reproductive systems use the cardiovascular system as its road or highway as far as distribution of things such as nutrients, oxygen, waste products, hormones, drugs, etc. There are many risk factors for an unhealthy cardiovascular system. Some diseases associated are typically labeled uncontrollable or controllable. The main uncontrollable risk factors are age, gender, and a family history of heart disease, especially at an early age. The cardiovascular system also contains sensors to monitor blood pressure called baroreceptors that work by detecting how stretched a blood vessel is. This information is relayed to the medulla oblongata in the brain, where action is taken to raise or lower blood pressure via the autonomic nervous system. The lymphatic system. The lymphatic system has three principal roles. First is the maintenance of blood and tissue volume. Excess fluid that leaves the capillaries when under pressure would build up and cause edema. Secondly, the lymphatic system absorbs fatty acids and triglycerides from fat digestion so that these components of digestion do not enter directly into the bloodstream. Third, the lymphatic system is involved in defending the body against invading microbes and the immune response. This system assists in maintenance, such as bone and muscle repair after injuries. Another defense is maintaining the acidic pH of urine to fight infections in the urinary system. The tonsils are our body's helpers to defend us against infections and toxins absorbed from the digestive tract. The tonsils also protect against infections entering into our lungs. The respiratory system. The respiratory system works in conjunction with the cardiovascular system to provide oxygen to cells within every body system for cellular metabolism. The respiratory system also removes carbon dioxide. Since carbon dioxide is mainly transported in the plasma as bicarbonate ions, which act as a chemical buffer, the respiratory system also helps maintain proper blood pH levels, a fact that is very important for homeostasis. As a result of hyperventilation, carbon dioxide is decreased in blood levels. This causes the pH of body fluids to increase. If acid levels rise above 7.45, the result is respiratory alkalosis. On the other hand, too much carbon dioxide causes pH to fall below 7.35, which results in respiratory acidosis. The respiratory system also helps the lymphatic system by trapping pathogens and protecting deeper tissues within. Note that when you have increased thoracic space, it can provide abdominal pressure through the contraction of respiratory muscles. This can assist in defecation. The organs of the respiratory system include the nose, pharynx, larynx, trachea, bronchi, and lungs. Together, these organs permit the movement of air into the tiny, thin-walled sacs of the lungs called alveoli. It is in the alveoli that oxygen from the air is exchanged for the waste product carbon dioxide, which is carried to lungs by the blood so that it can be eliminated from the body. Digestive system. Without a regular supply of energy and nutrients from the digestive system, all body systems would soon suffer. The digestive system absorbs organic substances, vitamins, ions, and water that are needed all over the body. In the skin, the digestive tract provides lipids for storage in the subcutaneous layer. Note that food undergoes 3 types of processes in the body: digestion, absorption, and elimination. If one of these is not working, you will have problems that will be extremely noticeable. Mechanics of digestion can include chemical digestion, movements, ingestion, absorption, and elimination. In order to maintain a healthy and efficient digestive system, we have to remember the components involved. If these are disturbed, digestive health may be compromised. Pathways that alter homeostasis. A variety of homeostatic mechanisms maintain the internal environment within tolerable limits. Either homeostasis is maintained through a series of control mechanisms, or the body suffers various illnesses or disease. When the cells in the body begin to malfunction, the homeostatic balance becomes disrupted. Eventually, this leads to disease or cell malfunction. Disease and cellular malfunction can be caused in two basic ways: either deficiency, cells not getting all they need, or toxicity, cells being poisoned by things they do not need. When homeostasis is interrupted in your cells, there are pathways to correct or worsen the problem. In addition to the internal control mechanisms, there are external influences based primarily on lifestyle choices and environmental exposures that influence our body's ability to maintain cellular health. Nutrition. If your diet is lacking in a specific vitamin or mineral, your cells will function poorly, possibly resulting in a disease condition. For example, a menstruating woman with inadequate dietary intake of iron will become anemic. Lack of hemoglobin, a molecule that requires iron, will result in reduced oxygen carrying capacity. In mild cases, symptoms may be vague, such as fatigue, but if the anemia is severe, the body will try to compensate by increasing cardiac output, leading to palpitations and sweatiness and possibly heart failure. Toxins. Any substance that interferes with cellular function, causing cellular malfunction. This is done through a variety of ways: chemical, plant, insecticides, and/or bites. A commonly seen example of this is drug overdoses. When a person takes too much of a drug, their vital signs begin to waver, either increasing or decreasing. These vital signs can cause problems, including coma, brain damage, and even death. Psychological. Your physical health and mental health are inseparable. Our thoughts and emotions cause chemical changes to take place, either for better as with meditation, or worse as with stress. Physical. Physical maintenance is essential for our cells and bodies. Adequate rest, sunlight, and exercise are examples of physical mechanisms for influencing homeostasis. Lack of sleep is related to a number of ailments such as irregular cardiac rhythms, fatigue, anxiety, and headaches. Genetic and reproductive. Inheriting strengths and weaknesses is part of our genetic makeup. Genes are sometimes turned off or on due to external factors, which can have some control over, but at other times, little can be done to correct or improve genetic diseases. Beginning at the cellular level, a variety of diseases come from mutated genes. For example, cancer can be genetically inherited or can be caused due to a mutation from an external source, such as radiation, or genes altered in a fetus when the mother uses drugs. Medical. Because of genetic differences, some bodies need help in gaining or maintaining homeostasis. Through modern medicine, our bodies can be given different aids, from antibodies to fight infections, or chemotherapy to kill harmful cancer cells. Traditional and alternative medical practices have many benefits, but, like any medical practice, the potential for harmful effects is present. Whether by nosocomial infections or a wrong dosage of medication, homeostasis can be altered by that which is trying to fix it. Trial and error with medications can cause potential harmful reactions and possibly death if not caught soon enough. The factors listed above all have their effects at the cellular level, whether harmful or beneficial. Inadequate beneficial pathways, a deficiency, will almost always result in harmful waiver in homeostasis. Too much toxicity also causes homeostatic imbalance, resulting in cellular malfunction. By removing negative health influences and providing adequate positive health influences, your body is better able to self-regulate and self-repair, thus maintaining homeostasis. Homeostasis throughout the body. Each body system contributes to the homeostasis of other systems and of the entire organism. No system of the body works in isolation, and the well-being of the person depends upon the well-being of all the interacting body systems. A disruption within one system generally has consequences for several additional body systems. Here are some brief explanations of how various body systems contribute to the maintenance of homeostasis. The nervous system. Since the nervous system does not store nutrients, it must receive a continuous supply from blood. Any interruption to the flow of blood may bring brain damage or death. The nervous system maintains homeostasis by controlling and regulating the other parts of the body. A deviation from a normal set point acts as a stimulus to a receptor, which sends nerve impulses to a regulating center in the brain. The brain directs an effector to act in such a way that an adaptive response takes place. If, for example, the deviation was a lowering of body temperature, the effector acts to increase body temperature. The adaptive response returns the body to a state of normalcy, and the receptor, the regulating center, and the effector temporarily cease their activities. Since the effector is regulated by the very conditions produced, this process is called control by negative feedback. This manner of regulating normalcy results in a fluctuation between two extreme levels. Not until body temperature drops below normal do receptors stimulate the regulating center, and effectors act to raise body temperature. Regulating centers are located in the central nervous system, the brain and spinal cord. The hypothalamus is a portion of the brain particularly concerned with homeostasis. It influences the action of the medulla oblongata, a lower part of the brain, the autonomic nervous system, and the pituitary gland. The nervous system has two major portions, the central nervous system and the peripheral nervous system. The peripheral nervous system consists of the cranial and spinal nerves. The autonomic nervous system is part of the peripheral nervous system and contains motor neurons that control internal organs. It operates at the subconscious level and has two divisions, the sympathetic and parasympathetic systems. In general, the sympathetic system brings about those results we associate with emergency situations, often called fight or flight reactions. The parasympathetic system produces those effects necessary to our everyday existence. The endocrine system. The endocrine system consists of glands which secrete hormones into the bloodstream. Each hormone has an effect on one or more target tissues. In this way, the endocrine system regulates the metabolism and development of most body cells and body systems. To be more specific, the endocrine system has sex hormones that can activate sebaceous glands, development of mammary glands, alter dermal blood flow, and release lipids from adipocytes. MSH can stimulate melanocytes on our skin. Our bone growth is regulated by several hormones, and the endocrine system helps with the mobilization of calcitonin and calcium. In the muscular system, hormones adjust muscle metabolism, energy production, and growth. In the nervous system, hormones affect neural metabolism, regulate fluid electrolyte balance, and help with reproductive hormones that influence CNS development and behaviors. In the cardiovascular system, we need hormones that regulate the production of red blood cells, which elevate and lower blood pressure. Hormones also have an anti-inflammatory effect and stimulate the lymphatic system. In summary, the endocrine system has a regulatory effect on basically every other body system. Thermoregulation. The living body has been characterized with a number of automated processes, which make them self-sustainable in the natural environment. Among these many processes are that of reproduction, adjustment with external environment, and instinct to live, which are gifted by nature to living beings. The survival of living beings greatly depends on their capability to maintain a stable body temperature, irrespective of the temperature of the surrounding environment. This capability of maintaining body temperature is called thermoregulation. Cold-blooded animals, such as reptiles, have somewhat different means of temperature regulation than warm-blooded or homeothermic animals such as humans and other mammals. This section is most relevant when considering warm-blooded organisms. Body temperature depends on the heat produced minus the heat lost. Heat is lost by radiation, convection, and conduction, but the net loss by all three processes depends on a gradient between the body and the outside. Thus, when the external temperature is low, radiation is the most important form of heat loss. When there is high external temperature, evaporation is the most important form of heat loss. The balance of heat produced and heat lost maintains a constant body temperature. However, temperature does vary during the day, and this set point is controlled by the hypothalamus. Body temperature is usually about 37.4 degrees C, but does vary during the day by about 0.8 degrees C. The lowest daily temperature is when the person is asleep. Temperature receptors are found in the skin, the great veins, the abdominal organs, and the hypothalamus. While the ones in the skin provide the sensation of coldness, the hypothalamic temperature receptors are the most important. The core body temperature is usually about 0.7 to 1 degrees C higher than the axillary or oral temperature. When body temperature drops due to external cold, an important component of protection is vasoconstriction of skin and limb blood vessels. This drops the surface temperature, providing an insulating layer, such as the fat cell layer, between the core temperature and the external environment. Likewise, if the temperature rises, blood flow to the skin increases, maximizing the potential for loss by radiation and evaporation. Thus, if you dilated the skin blood vessels by alcohol ingestion, this might give a nice warm glow, but it would increase heat loss if the external temperature was still low. The major adjustments in cold are to shiver to increase heat production and constrict blood vessels in the periphery and skin. This helps to minimize heat loss through the skin and directs blood to the vital internal organs. Besides the daily variation in body temperature, there are other cyclic variations. In women, body temperature falls prior to ovulation and rises by about 1 degree C at ovulation, largely due to progesterone increasing the set point. Thyroid hormone and pyrogens also increase the set point. The basal metabolic rate, or BMR, is about 30 calories per square meter per hour. It is higher in children than in adults, partly as a result of different surface area to body mass ratio. Due to this relationship, young children are more likely to drop their temperature rapidly. There is greater temperature variation in children than in adults. It is increased by thyroid hormone and decreased by thyroid hormone lack. Different foods can affect BMR, and the respiratory quotient of foods differ. carbohydrate is 1, protein 1, fats 0.7. Blood pressure is expressed as two different numbers. The first number is called the systolic blood pressure, and the second is the diastolic blood pressure. Systolic blood pressure is the pressure at the time of the cardiac cycle when the heart contracts, forcing blood out. This is called systole. This is the time of greatest pressure. The diastolic number comes from the time in the cardiac cycle when pressure is at its lowest, while the heart is refilling with blood. This phase is called diastole. The blood pressure in large arteries is about 120 over 80 millimeters of mercury. By the time this comes to the capillaries, it has partly lost its pulsatile nature and has a pressure of about 35 millimeters of mercury. This pressure falls rapidly along the capillary to 15 millimeters of mercury at the venous end. This hydrostatic pressure tends to force fluid out of the capillary into the interstitium, the space between cells, but balance is maintained by the colloid osmotic pressure due to proteins, principally albumin, at 26 millimeters of mercury. Net water movement is small, about 2%, and thus colloid osmotic pressure is the same at the arterial and venous end of the capillary. At the arterial end of the capillary, there is a net outward force of about 11 millimeters of mercury, while at the venous end of the net inward force is about 9 millimeters of mercury. There is an imbalance between water movement out and movement back in, which leads to an imbalance of about 3 liters per day, which is removed as lymph. There is some albumin in the interstitial tissue, and it varies in different organs, but the concentration may be up to 10 or 20% of plasma. This gives an interstitial oncotic pressure, which causes movement of fluid into the interstitium. However, the bulk movement of water is not the way nutrients get to cells. Nutrients diffuse down their concentration gradient, as the capillary is very permeable to all small molecules. The extracellular volume is approximately 13 liters in a 70 kilogram person. 10 liters are in the interstitial space, and 3 liters in plasma. The capillaries are the interface between the two compartments and are permeable to most substances with a molecular weight less than 20,000. Thus, nutrients can readily diffuse across the wall and go from blood to cell. Despite the high permeability of the capillary, water is maintained inside due to the oncotic pressure, and only about 2% of the plasma flowing through the capillary moves across the wall. Dehydration and volume depletion. Plasma osmolality is about 290 milliosmoles per liter, contributed mainly by sodium, 140 millimolar per liter, and its accompanying anions. In dehydration, water is lost from the body. The rise in osmolality that occurs in the plasma, also sodium rises, causes water to initially move out of the cells along the osmotic gradient. Thus, cell volume is initially reduced, but cell homeostatic processes subsequently return it towards normal by taking up solute. In dehydration, water is removed from the plasma, and thus hematocrit and albumin, which have not been lost, have a higher concentration. In volume depletion, water and electrolytes are both lost, and thus there will be little effect on either sodium concentration or osmolality. As osmolality is not altered, there will be no force to pull water out of the cells, and cell volume is not affected. In volume depletion due to blood loss, the hematocrit acutely is the same, but the resultant fall in blood pressure causes fluid to come out of the interstitium into the vascular component, and albumin and hematocrit both decrease. When there is volume depletion due to electrolyte and water loss by vomiting or diarrhea, there will be little or no effect on plasma osmolality or sodium concentration. However, there will be a small increase in hematocrit and plasma albumin because the volume is lost from the extracellular space, and as blood cells and albumin are not lost, this increases the concentration. In volume depletion, forces are activated that retain sodium and water in the body. The sodium retention works to a major extent by the renin-angiotensin-aldosterone system, which is activated by a fall in blood pressure caused by volume depletion. In dehydration, the high osmolality activates ADH secretion, which causes water retention. As there is also volume depletion, this activates the renin-angiotensin-aldosterone system, which causes sodium to be retained. This retention would tend to cause a rise in sodium concentration, which is already high, but the water retention would correct this. There is no effective receptor that monitors and controls sodium concentration by altering sodium excretion. Sodium-retaining hormones are predominantly regulated by the volume and blood pressure. Initially, in blood loss, the hematocrit is not altered, but falls as fluid comes in from the interstitial space. Water balance. Vasopressin, also called antidiuretic hormone, is the principal compound controlling water balance by decreasing water output by the kidney, and thus decreased urination. It perceives the need by monitoring plasma osmolality, and if this is high, vasopressin is secreted. Vasopressin is formed in the hypothalamus and travels down axons to the pituitary, where it is stored. Plasma osmolality is the usual factor regulating vasopressin release, but other factors alter the release. Pain and emotion release vasopressin together with the other posterior pituitary hormone, oxytocin. Alcohol inhibits the release of vasopressin and thus causes diuresis. A low plasma volume also releases vasopressin, which in high concentration can cause vasoconstriction. these different factors can overcome the usual physiological control of osmolality. Osmoreceptors in the hypothalamus monitor the plasma osmolality and send a signal down the axon that releases vasopressin from the posterior pituitary gland. Vasopressin travels by the blood to the kidney and binds to a receptor on the basolateral membrane. By a series of cellular events, alters the permeability of the luminal membrane to water, thereby increasing the water permeability of the collecting duct, and due to osmotic gradients created in the kidney, causes water to be retained by the body, which is antidiuresis. This provides the other name for vasopressin of antidiuretic hormone. Vasopressin released by the pituitary gland binds to a receptor on the basolateral membrane and activates adenyl cyclase, which increases cyclic AMP levels in the kidney. Thus, by a series of reactions, some of which involve calcium, causes microfilaments to contract and insert pre-formed water channels, aquaporins, into the luminal membrane, thus increasing water permeability. A high plasma osmolality is the important physiological stimulus causing vasopressin release. Urea in plasma in a normal person only has a concentration of 6 millimolar per liter, and thus contributes to only a small part of plasma osmolality. Even if plasma urea is elevated to 30 millimolar per liter, it would not have a significant effect on vasopressin release, as membranes, including those of the osmoreceptor cells, are permeable to urea. If there is excessive ADH, water is retained and the osmolality and sodium concentration would fall, hyponatremia. If there is no ADH, water is lost, and osmolality and sodium concentration would rise, hypernatremia. While ADH is released, if the plasma volume falls, the most important factor to restore volume is retention of sodium by the renin, angiotensin, aldosterone, and other salt-retaining systems. Human physiology, sodium balance. Sodium is an important cation distributed primarily outside the cell. The cell's sodium concentration is about 15 millimolar per liter, but this varies in different organs, and with an intracellular volume of 30 liters, about 400 millimolar are inside the cell. The plasma and interstitial sodium is about 140 millimolar per liter, with an extracellular volume of about 13 liters. 1800 millimolar are in the extracellular space. The total body sodium, however, is about 3700 millimolar, as there is about 1500 millimolar stored in bones. The usual sodium intake of an Australian diet is about 180 millimolar per day, but varies widely, between 50 and 400 millimolar per day, depending on habit and cultural influences. The body has potent sodium-retaining mechanisms, and even if a person is on 5 millimolar of sodium a day, they can maintain sodium balance. Extra sodium is lost from the body by reducing the activity of the renin-angiotensin-aldosterone system, which leads to increased sodium loss from the body. Sodium is lost through the kidneys, sweat, and feces. In states of sodium depletion, aldosterone levels increase, and in states of sodium excess, aldosterone levels decrease. The major physiological controller of aldosterone secretion is the plasma angiotensin II level, which increases aldosterone secretion. A high plasma potassium also increases aldosterone secretion, because besides retaining sodium, high plasma aldosterone causes potassium loss by the kidney. Plasma sodium levels have little effect on aldosterone secretion. A low renal perfusion pressure stimulates the release of renin, which forms angiotensin I, which is then converted to angiotensin II. Angiotensin II will correct the low perfusion pressure by causing constriction of blood vessels and by increasing sodium retention by a direct effect on the proximal renal tubule and by an effect operated through aldosterone. The perfusion pressure to the adrenal gland has little direct effect on aldosterone secretion, and the low blood pressure operates to control aldosterone via the renin-angiotensin system. In addition to aldosterone and angiotensin II, other factors influence sodium excretion. Thus, in high sodium states due either to excess intake or cardiac disease, atrial peptide is secreted from the heart and by a series of actions causes loss of sodium by the kidney. Elevated blood pressure will also tend to cause sodium loss, and a low blood pressure usually leads to sodium retention. Aldosterone also acts on the sweat ducts and colonic epithelium to conserve sodium. When aldosterone has been activated to retain sodium, the plasma sodium tends to rise. This immediately causes release of ADH, which causes water to be retained, thus retaining sodium and water in the right proportion to restore plasma volume. Potassium balance. Potassium is predominantly an intracellular ion, and most of the total body potassium of about 4,000 millimolar is inside the cells, and the next largest proportion, 300 to 500 millimolar, is in the bones. Cell potassium concentration is about 150 millimolar per liter, but varies in different organs. Extracellular potassium is about 4 millimolar per liter, and with an extracellular volume of about 13 liters, 52 millimolar, less than 1.5%, is present here, and only 12 millimolar in the plasma. In an unprocessed diet, potassium is much more plentiful than sodium and is present as an organic salt, while sodium is added as NaCl. In a hunter-gatherer, potassium intake may be as much as 400 millimolar per day, while in the Western diet it is 70 millimolar per day, or less if a person has a minimal amount of fresh fruit and vegetables. Processing of foods replaces potassium with sodium chloride. While the body can excrete a large potassium load it is unable to conserve potassium. On a zero potassium intake, or in a person with potassium depletion, there will still be a loss of potassium and 30 to 50 millimolar per day in the urine and feces. If there is a high potassium intake, for example, 100 millimolar, this would potentially increase the extracellular potassium level 2 times before the kidney could excrete the extra potassium. The body buffers the extra potassium by equilibrating it within the cells. The acid-base status controls the distribution between plasma and cells. A high pH, alkalosis, the pH greater than 7.4, favors movement of potassium into the cells, while a low pH, or acidosis, causes movement out of the cell. A high plasma potassium increases aldosterone secretion, and this increases the potassium loss from the body, restoring balance. This change of distribution with the acid-base status means that the plasma potassium may not reflect the total body content. Thus, a person with an acidosis and a plasma potassium of 6.5 millimolar per liter could be depleted of total body potassium. This occurs in diabetic acidosis. Conversely, a person who is alkalotic with a plasma potassium of 3.4 millimolar per liter may have normal total body potassium.